Dear students, the next lecture on piping supports is about the codes which are in place for uh, piping supports, and we will also discuss a few cases or specific scenarios on how the piping supports are installed. First is the requirements of the piping supports as per ASME B31.3 code. ASME B31.3 is for all process piping, and the requirements as per this ASME B31.3 code is there should not be any leakage because of the pipe support installation. If we are installing any pipe supports, it should not damage the main pipeline, and there should not be any leakage due to the installation of this pipe support. Normally, leakages will arise due to the corrosion problems, and when we install the pipe supports by using some clamps or bolted arrangements, we may damage the main pipeline, or uh, the requirements as per ASME B31.3 is that there should not be any leakage because of installing any pipe support. Next is when we install a pipe support, it should not add additional thrust or movement on the connected equipment and structure. Suppose if we are installing a pipe support incorrectly, then there might be disorientation of the pipe routing. So it may create some excessive thrust or bending moments or movements on the lateral sides on the connected equipment and the structure. So this will disturb the entire orientation or the layout plan. So as per ASME B31.3, the installation of the pipe supports should not induce any excessive thrust or movement on the connected equipment and structure. Next is that after installing the support, there should not be any disengagement of the piping from its support. For example, if you are installing a shoe support for a inclined pipeline, because of the installation of the shoe support, if we do not focus on the proper angle of inclination, then we can see that the pipeline will be disengaged from the support, and it can fall because of the action of gravity on the load of the pipe. So if we do not follow a proper angle of inclination and the installation of a shoe support, in the case of an inclined pipeline, the disengagement of the piping will happen from its support. So the support, instead of doing its original function, it will accelerate the descent of the pipeline along a slope. So this kind of scenarios should be avoided, and after installing the support, there should not be any disengagement of the piping from its support. Another example I can give you is improper installation of the hanger supports, because hanger supports are normally placed at a higher altitude. So when we have hanger supports that may not be installed properly, the additional swaying of the pipeline can happen. Because of that, the inducing moments on the structure will happen. So the disengagement of the piping along the support can happen. So after installing the support such as a hanger support, we should the support should be stiff enough to hold the entire weight of the piping, and it should prevent the swaying of the piping due to seismic loads or occasional wind loads or vibration and so on. Next is the withstand fluid induced vibration. When the pipelines are transporting the fluids at a high velocity, there can be cavitation happening because of throttling or because of water hammer effects. The designed support should withstand all the fluid induced vibration when the fluid is hitting on any pipe bends or elbows, or the change in direction of the pipe routing. In all such cases, the fluid will hit the pipeline with greater velocity. So this will induce vibration, and all the designed supports should withstand the fluid induced vibration. Next is a very important point which is being repeated in each of these lecture slides. We have to definitely consider the thermal expansion or contraction while designing a pipe support system, and the type of pipe support should promote any heat loss or gain from the environment. So as per the ASME B31.3, these are the guidelines or the requirements for the pipe supports which are installed to support the load on the piping. Next, we will look at some codes which are followed worldwide for the pipe support systems. First is the ASME 31.3 and 31.1. These are used for power piping and process piping standards. Next is the MSS SP58. These are focusing on the hangers and the support materials design and manufacture, commonly followed in USA. Then MSS SP69. So this is also focusing on the pipe hangers and supports, the selection and application of the various pipe hangers and supports. 58 is for the materials, then design and manufacture, and MSS SP69, the ANSI MSS edition, will be focusing on the selection and application of the various pipe hangers and supports. Then MSS SP77 will focus on the guidelines for pipe support contractual relationships, normally followed in the USA. For example, in a process plant, the piping may be installed by a EPC company and the supports may be provided by another company. So, in such case, the contractual relationships for the pipe support installation or the guidelines for that will be followed by MSS SP77 guidelines. Next is the fabrication and installation practices for pipe hangers and supports. MSS SP89 guidelines gives the fabrication and installation practices of pipe hangers and supports. Next is the MSS SP90. This is for the terminology of pipe hangers and supports. Then MITI 501 is a technical regulation in Japan for pipe supports installation, manufacture, and fabrication. Then BS 3974, it is a specification for pipe supports in the UK. Then RCCM, it's a specification for pipe supports applicable in France. Then VGBR 510L, this is a standard support guidelines followed in Germany. So as we look at the different locations worldwide, the standards for the pipe supports are also varying uh, at different locations worldwide. So as per the codes and standards, we need to follow these guidelines when we are installing the pipe support and choosing the material of construction, the design, fabrication and installation practices, and the standard support guidelines that needs to be followed by these codes and standards. So now we will look at a few cases where the support systems, how they are installed in the process plant. So here you have a pump which is connected to the drive assembly, and on this pump the hot pump suction nozzle is placed, which is connected with a valve to regulate the flow, and the downstream section is connected to the further sections of the process plant. So here we have a control valve which is in the main suction line uh, of this pump. So here we need to support this control valve which is placed near a hot pump suction nozzle. So as we discussed earlier, we can see that this additional control valve can put excessive stress on the nozzle of the pump. So we need to prevent the failure of this nozzle. So in order to prevent that failure of this nozzle, reinforcement pads may not be a proper alternative, uh, because the reinforcement pads can get damaged due to the vibratory loads and the temperature generated or the heat energy generated due to this drive assembly. So we need to install a trunnion support. So as you know, trunnion support is a support which is a pivoted kind of a support. So if you see this picture, the drive assembly and the heavy machinery which will cause a lot of vibration are placed on a platform, and that platform is again placed on a civil structure with a strong foundation. So all the vibratory loads will be taken care by this plate and the civil structure, and the subsequent vibrations which may arise in this nozzle will be transported in the suction line of this pump. So to prevent this pipeline failure and the nozzle failure, we need to support this pipeline uh, with a trunnion support. So trunnion support is, as I told you, is a pivot kind of a support. Here we do not consider the rotatory movement. We are only interested to curtail the movement of the pipeline in the horizontal and in the lateral movements. So trunnion support is suitable. And as per a previous guideline, I explained that the valve is a heavy component. So the support should be located as close to this valve as possible. So this insulated trunnion support is present on a civil foundation, and it is attached to the suction nozzle near to this valve. The trunnion can contract due to the cooling, which may lead to the separation from the nozzle and transfer the load to the nozzle itself. So to avoid that scenario, we are insulating the trunnion. In this case, the excessive stress on the nozzle caused by the weight of the valve and the heat energy transport on this suction line may not be translated to the trunnion, and it may prevent the additional stress buildup. So when a non-insulated trunnion is used, it can cause the uh, cooling and separation from the nozzle. So we will look at an insulated trunnion support for this particular kind of an application. Next scenario which we are going to focus is a supporting line from a short vessel and a supporting line from a tall vessel. So short vessels, the amount of buckling is actually very less. Buckling is very common for long and columns with a smaller diameter. So in the case of a supporting line from a short vessel, if you look at this scenario, when you are connecting a pipe to the top nozzle of a short vessel with similar material and operating temperature, we have to provide a single ground level support that will be often sufficient, because this short vessel will be supported using any skirt support or lug supports and so on. So the entire weight of this vessel along with this nozzle and the top load of this line will be supported on this uh, vessel support. So we have to look at only the loads that may be induced on this vertical section of the pipeline. So as we discussed in previous slides, we have to provide the support as close as possible where the pipeline is changing its direction. So following that guideline, we have to locate a ground level support which is on a level platform to support this pipeline which is connected from the top nozzle. And also we have to provide certain restraints to avoid the vibrations, because the on the vertical section when the fluid flow is happening, there may be vibrations. So in order to have a uniform spacing of the piping from this short vessel, we may also install certain additional supports connected to the main short vessel, as you see in the picture. So you can see that there are two supports which are attached to this vertical section. Those two sections are attached to the main short vessel, and as the pipeline changes its direction, we are installing a support to minimize the thermal expansion, and the inherent flexibility of the pipeline will also be used to accommodate the thermal expansion. This approach actually simplifies the support design, and it reduces the cost of supporting. So, and also you can see that the pump is placed on a level civil foundation, and the civil foundation is also having the same height as that of the pipeline support. So we should not disorient this pipeline by providing different heights for the support and the platform for the pump. So those two things are at the same level when considering the uh, installation of the support, and the support is installed as close as possible to the bend section where the pipeline is changing its direction. So now we will move on to a supporting line from a tall vessel. So in this case, when connecting a pipe to a tall vessel with a lot of significant temperature differences, for example, you may consider an atmospheric distillation column which processes crude oil. So in this case, there are different zones of temperature, or the various fractions of petroleum are actually got from different side draws. So the temperature range is very significant in this kind of tall columns where different fractions are taken from side draws. In such a scenario, when we are connecting a pipe to a tall vessel with a lot of significant temperature differences, the thermal expansion of the vessel can induce stress on the piping. So to mitigate this, we will do the stress analysis and support the piping at a neutral point near the nozzle connection. So we can see that the piping is supported at some neutral points. Neutral points is a very uh, it's a a technical jargon. Uh, we consider this neutral point as this where the stresses are minimal, or they are balanced properly. So here in this case of a tall column, you can see that the vertical pipe section is connected at different locations, and it may require a lot of connections from this tall vessel to support this vertical section. And when the line is changing its direction, we are also installing a support which connects this line to the pump. Then additionally, we may also use expansion loops near the pump or at the top of the vessel to accommodate for further thermal movement. So here you can see that there is an expansion loop which connects to the top of this nozzle. And similarly, in this picture also, near to the pump, we do not directly use the routing to connect to the pump. We use an expansion bend to accommodate for the thermal movement. Because of the significant temperature differences on the different sections of the column, we have to accommodate for those thermal expansion by using expansion loops near to the pump as also near to the top nozzle. So this is about supporting lines from short vessels and supporting lines from tall vessel. So these two are actually two different scenarios where buckling is significant in tall columns, but it may not be a significant factor for short vessels. Next case scenario, we are going to look at the installation of fixed supports. Here you look at there are actually pumps which transport the fluid, and if you are going to connect a pipeline directly to two different pumps, from two different pumps, the this is a storage vessel from which you connect a pipeline, and the pipeline is connected to two pumps. So these pumps will transport the fluid to different locations. Here it is advisable to install a fixed support near to in sorry, a fixed support on this horizontal vessel. So you also have to look at the connection to the vessel, and near to that connection we install a fixed support. That is, in this picture you can see that the connection is not exactly at the center of this horizontal vessel, but it is somewhere on one side of the vessel. So we will install a fixed support near to that connecting end, and the other routing is connected to the pump 1 and pump 2. So this is about a case 1 where we install a fixed support. Next is case 2. Here there is a pipeline which is connecting to a pipe rack line. So the pipe rack line is located at a certain distance, and because of the length of the pipeline going to the pipe rack line, we have to install a fixed support on the other end of the horizontal vessel. So this entire span of the pipeline needs to be connected through the pipe rack line. So the fixed support is placed in such a manner that it is at a convenient strategic location to accommodate for this entire pipeline span, and also the load induced by this vessel. Next is about the installation of support for different line sizes. Here there is a 20-inch line which is getting attached to this vessel, and this 20-inch line is attached to this vessel, and one more line is of 8 inches that is connected to two pumps. So here also we have to look at the load induced by the 20-inch line, and near to this 8-inch line we need to install the fixed support on the to support this horizontal vessel. So these are three different cases where the supports are located. In the case of storage drums, which may connect to a pipe rack line or which may connect to pumps, and for different line sizes. Next is the load calculation analysis guideline. So this is a short table, or we will consider different scenarios where the load calculation may be required, and the computer analysis might be required for certain cases, or we can go for simplified calculation methods without any computer analysis in certain cases, and in certain cases we may require no analysis at all. So for the load calculation analysis guideline, first we look at the type of the line. So first is the pumps. If you look at the notes at the legend 1, if we have 3 or more pumps in the layout, then we need to go for computer analysis in the case of load calculation, because we may not know the interference of the vibrations on the load intensity on the lines. So if you have pumps when the line size is less than 2 inch, then if it is below 0 degrees, then we can go for a simplified calculation method. Then in the case of 1 to 100, no analysis might be required, and above 100, if we look at the 200 degrees centigrade or above, then we need to go for computer based analysis. Then in the case of 3 to 4 inches below 0 degrees, we have to go for computer based analysis for a temperature range of minus 30 degrees centigrade and below. Then in the range of 1 to 100 degrees, we may go for simplified calculation methods or computer based analysis, and above 100 degrees we should go for computer based analysis. Then for all the pump lines which are greater than 4 inches, we have to go for computer based analysis for all the temperature ranges below 0 or above 100 or in between 1 to 100. Next is the turbines. For all these line sizes, we may not go for any analysis, or we do not have sufficient data. Depending upon case by case, we need to go for the analysis of computers, using computers or not. Then compressors and blowers less than 2 inches, we go for simplified calculation methods for all the temperature ranges. Then for greater than 2 inches, we have to go for computer based analysis. Then air coolers, all the line sizes, when we have the temperature range between 1 to 100 and above 100, we go for computer based analysis. Below 0 degrees, we may not require any analysis at all. Then transfer lines and reactor lines, for all line sizes greater than 100 degrees, we may require computer based analysis. Then jacketed lines below 0 degrees, we have to go for computer based analysis, and above 100 degrees, we have to go for computer based analysis. Then in the case of storage tanks with large tank settlements greater than 2 inch, then we go for computer based analysis for all the scenarios. Then lines which may be subjected to vibration less than 2 inches, we can go for simplified calculation methods. But above 100 degrees, we have to go for computer based analysis. And for all the lines greater than 2 inches, we require computer based analysis for the temperature ranges below 0 or above 100 and between 1 to 100. Then safety and relief discharge lines less than 4 inches, we go for standardized calculation methods below 0 and 1 to 100s. But above 100 degrees, we may go for standard calculations up to 300 degrees, and computer based calculations for more than 300 degrees. Then safety and discharge lines, we have to see the effect of reaction forces due to valve discharge. So for greater than 4-inch lines, all the temperature ranges, we have to go for computer based analysis. Then the systems which may operate under multi-operating and cyclic conditions, for less than 2 inches, we may go for simplified calculation methods. And for 1 to 100, no analysis is required. And for above 100, we go for simplified calculation methods. For greater than 2-inch lines, below 0, we have to go for computer based analysis. Then for 1 to 100 degrees, we go for standard calculation methods. Then above 100, we go for computer based analysis. Then in the case of other scenarios which are not covered in this table, uh, for less than 2-inch lines, we normally do not perform any analysis. Then for 3 to 4 inches, depending upon the temperature range less than minus 30 degrees, we go for the computer based analysis. Then more than near 0 degrees, we go for simplified calculation methods. Then 1 to 100, simplified calculation methods. For above 100, we have to look at the temperature range. More than 300, we go for computer based analysis, and less than 300, we go for the simplified calculations. Same holds good for the 6 to 12-inch lines, and greater than 12-inch lines below 0 degrees, we have to go for computer based analysis. 1 to hundreds, we go for standard simplified calculation methods, and above 100 degrees, we have to go for computerized calculation methods. So this lecture provided you with some scenarios where how to install the supports, then the load calculation analysis on this different lines, because this is very important to decide upon the nature of the support and the location of the support. So this table summarizes the different types of lines and the how the scenarios will change depending upon the temperature and the size of the pipeline.